Before 1915, Newton's gravity reigned, an invisible force pulling objects together. It was a simple, elegant explanation that had stood the test of time for centuries. But then, Albert Einstein arrived, not just tweaking the rules, he rewrote them. He introduced a radical new way of thinking about the universe. His general relativity wasn't just about gravity, it was about the fabric of space and time itself. This was a groundbreaking shift in our understanding of the cosmos. Space and time, he said, are woven into a four-dimensional fabric, space-time. This fabric can be curved and warped by the presence of mass and energy. Imagine a giant, stretchy trampoline. Massive objects curve this fabric. The more massive the object, the deeper the curve. Gravity, in Einstein's view, is just the result of moving along these curves. Objects follow the paths dictated by the curvature of space-time. This idea was revolutionary and testable. Scientists could now design experiments to observe these effects. In 1919, astronomers saw starlight bend around the sun during an eclipse, just as Einstein predicted. This was a monumental confirmation of his theory. Suddenly, the universe wasn't just a stage, it was an active participant. The very fabric of reality was dynamic and alive. General relativity became the new law, describing gravity on the grandest scales. It opened up new realms of understanding about the cosmos. But Einstein's equations hinted at something even stranger. If enough mass is packed into a tiny space, it could create a dent so deep that nothing escapes. This was the theoretical birth of black holes. What kind of object could do that? The answer, a black hole. These mysterious objects would become one of the most fascinating predictions of general relativity. This prediction was so bizarre it took decades for science to catch up. The concept of black holes was initially met with skepticism and disbelief. The universe, it seemed, was hiding monsters in the math. These cosmic enigmas challenged our understanding of physics, and Einstein himself wasn't sure he believed in them, yet his equations were clear, and the implications were profound. Einstein's equations were barely dry, still echoing with the excitement of a new understanding of gravity, when Karl Schwarzschild, serving on the front lines of World War I, managed to do something extraordinary. He found the very first exact solution to Einstein's field equations, all while surrounded by the chaos of war. Schwarzschild described the space-time around a perfectly spherical mass, revealing a hidden structure in the universe, and discovered something wild and unexpected lurking in the math. If you squeeze enough mass into a small enough space, gravity becomes so intense that nothing, not even light, can escape its pull. The very fabric of space and time would be warped beyond recognition. This invisible boundary, where escape becomes impossible, is called the Schwarzschild radius, a point of no return. For the Sun, that radius is just 3 kilometers, an unimaginably tiny core compared to its true size. For Earth it's even smaller, the size of a peanut. Imagine all the mass of our planet crushed into something you could hold in your hand. This was the mathematical birth of the black hole, a point of infinite density, a singularity wrapped in darkness, where the known laws of physics break down. At first, physicists, including Einstein himself, thought this was just a strange mathematical oddity, a quirk of the equations rather than a real object. How could nature possibly create such an extreme object? Was it even possible for a star to collapse so completely? The idea of a star collapsing into a one-way door in the universe, a place where time and space end, seemed like pure science fiction, more at home in pulp novels than in real science. But the math was clear and relentless. Black holes were not just a fantasy, they were a real possibility waiting for evidence to prove their existence. The universe, it turned out, might be far stranger than anyone had ever imagined, filled with objects that defy our everyday experience. The question now was, could these cosmic monsters actually exist out there in the universe, or were they just theoretical phantoms? Or were they destined to remain nothing more than ghosts in the equations, haunting the minds of physicists for generations to come? You'd think Einstein would champion black holes. After all, his theory predicted them. But he was their biggest skeptic. The idea of a singularity, a point where physics breaks down, troubled him deeply. To Einstein, infinities in the math meant the theory was incomplete, not that nature allowed such absurdities. He believed some unknown law would prevent a star from collapsing into a black hole. In 1939, he even published a paper arguing black holes couldn't form. He thought matter could never be compressed enough to create an event horizon. Einstein was convinced black holes were just mathematical ghosts. Even the greatest minds can be led astray by intuition and philosophy. His gut told him the universe should be rational everywhere, but the math kept pointing to a different, stranger reality. Einstein, the reluctant father, refused to believe in his own cosmic monster. The event horizon, Einstein's nemesis, isn't a physical surface but a boundary in space-time. It's the invisible line that marks the point of no return around a black hole, a region where the pull of gravity becomes so overwhelming that nothing can escape its grasp, not even light itself. Cross it, and escape becomes impossible, no matter how fast you go. The laws of physics as we know them simply break down at this threshold, and the universe beyond is forever cut off from anything that falls inside. Inside, space-time is so warped that all paths lead to the singularity. The very fabric of reality is stretched and twisted, funneling everything inward toward a point of infinite density. Even light can't get out. Space itself is flowing inward faster than light can travel. It's as if the river of space-time rushes so swiftly that nothing can swim against its current. That's why black holes are black. Nothing, not even information, escapes. The event horizon acts as a cosmic veil, hiding whatever happens inside from the rest of the universe. The event horizon is a one-way door. Events inside are forever hidden from the universe. Once crossed, there's no turning back, and no signal can ever return. For someone falling in, crossing the horizon might feel uneventful, until the singularity looms. You wouldn't notice the exact moment you pass the boundary, but your fate would be sealed. But to a distant observer you'd appear to freeze and fade, never quite crossing over. Time seems to slow to a halt at the edge and you become a ghostly image, forever suspended at the brink. This difference in perspective is a direct result of warped space-time. The closer you get to the event horizon, the more time and space themselves become distorted, creating a bizarre and counterintuitive reality. The event horizon's one-way nature bothered Einstein. It seemed to break the rules of time and information. He struggled with the idea that information could simply vanish, lost to the universe forever. Yet it's a real physical boundary, not just a mathematical trick. Modern observations and simulations confirm that the event horizon is a fundamental feature of black holes. The universe, it turns out, is full of horizons we can never cross. From the edge of the observable universe to the boundaries around black holes, these limits define what we can know, and black holes are the ultimate example. Their event horizons are the most extreme boundaries, challenging our understanding of physics and the nature of reality itself. The event horizon is where our knowledge ends and mystery begins. It's a frontier that continues to fascinate scientists and inspire new questions about the universe. Einstein's discomfort was justified, but the boundary is real. The event horizon stands as a testament to the strange and wondrous nature of our cosmos, inviting us to keep exploring its secrets. The singularity at a black hole's center drove Einstein crazy. He saw infinities in the math as a sign the theory was incomplete. For years, physicists debated, was the event horizon itself a singularity, or just the center? Later they realized the event horizon's infinity was just a coordinate glitch, like the North Pole on a map. You can cross it without anything weird happening locally. The true singularity, the real breakdown, lies at the center, where physics as we know it fails. Modern physics accepts the event horizon as real, but the central singularity remains a mystery. Here, general relativity and quantum mechanics must unite. Einstein was right, singularities signal a problem with our theories, but he was wrong about where the problem lies. Einstein's biggest mistake? He thought black holes couldn't form in reality. He argued that collapsing matter would never reach the critical density for an event horizon. Meanwhile, Oppenheimer and Snyder showed that, for massive stars, collapse is inevitable. Einstein also misunderstood the event horizon, thinking it was a fatal flaw in the math. He couldn't accept a one-way membrane in space-time. Even geniuses have blind spots. Einstein set the rules but hesitated to follow them to their wildest conclusions. It took a new generation to embrace black holes as real. The monsters he doubted became the ultimate test of his theory. Sometimes, science moves forward by proving its greatest minds wrong. For decades, black holes were just theory, until the universe started revealing its secrets. In the 1960s, astronomers found quasars' brilliant beacons powered by supermassive black holes. Then came Cygnus X1, an invisible heavyweight tugging on a star, too massive to be anything but a black hole. The evidence piled up and Einstein's doubts faded. The real breakthrough came in 2015. LIGO detected gravitational waves from two black holes merging. We didn't just see the fireworks, we felt space-time itself ripple. Black holes were no longer ghosts, they were real, common, and crucial to the cosmos. Each new detection confirmed Einstein's equations, but disproved his skepticism. The universe had no problem making the monsters he thought impossible. Black holes shape galaxies, drive cosmic evolution, and test the limits of physics. The verdict was clear. Black holes exist, and they're everywhere. Einstein's theory predicted them, but the universe proved him wrong. Sometimes nature is bolder than even its greatest thinkers, and black holes are its boldest creation. Ironically, while Einstein doubted black holes, his theory describes them perfectly. Every observation, gravitational waves, the shadow of M87's black hole, matches his predictions. In 2019, we saw the first image of a black hole's shadow, just as Relativity described. Even the plunging region inside the event horizon behaves as his equations say. Black holes once denied are now the ultimate test of general relativity. The universe doesn't care what we believe, it follows the rules. And in the case of black holes, those rules are Einstein's. His map was flawless, even if he doubted the destination. Science can outgrow its creators, and sometimes the universe is the best teacher. So, what's the final score? Einstein was wrong about black holes' existence, but right about their nature. Black holes are everywhere, cosmic engines, not mathematical ghosts. Yet general relativity, his masterpiece, has passed every test. Science is a journey, not a destination. Einstein opened the door, but others, Schwarzschild, Oppenheimer, Hawking, walked through. No one, not even Einstein, gets everything right. Science corrects itself, that's its strength. His legacy is richer for his doubts. Black holes are now laboratories for the laws of physics. They push us to the edge of knowledge, just as Einstein did. The monsters he feared are now our greatest teachers. And the quest he began continues, deeper into the cosmos than he ever dreamed.